Welcome to Lesson 9D, Equations for Rayleigh Flow. In this lesson, we'll review all the equations we have so far for Rayleigh flow. I'll develop some new ones, and I'll show you how to use choked or sonic or critical conditions to solve these problems even when the flow is not choked. After I summarize all the equations, I'll do an example problem and show you how to use the compressible aerodynamics calculator for Rayleigh flow. Here's a summary of the equations we have so far: mass, momentum, energy, TdS equation, ideal gas law, and when you have choked conditions, the maximum possible heat transfer. Let's develop some more equations that we'll need. Let's start with our momentum equation, but let's rewrite rho v squared as rho a squared m squared, since m is v over a, and since a squared is gamma RT for an ideal gas, but rho RT is P by our ideal gas law. So rho v squared is gamma P m squared. Plugging this into here in both places, our momentum equation reduces to P plus gamma P m squared on both sides. And after a little bit of rearrangement, P2 over P1 becomes 1 plus gamma m1 squared over 1 plus gamma m2 squared. I'll call this equation 1. Alert students may recognize that this is the same Rayleigh equation for pressure ratio that we had previously when we derived the Rayleigh curve talking about normal shocks. This equation holds between any 2 points on the Rayleigh curve. Also note that for a given state 1 with Mach number m1, m2 approaches sonic conditions as we increase the heat transfer rate, whether the flow is subsonic or supersonic. In other words, we can be on either the subsonic or the supersonic branch on the Rayleigh curve, and as we keep increasing heat, we go towards critical or sonic conditions, which we indicate with the superscript star or asterisk, as we've discussed previously. I'll resketch the Rayleigh curve, as we've sketched several times, with the 2 branches and the sonic or critical conditions at maximum entropy. And I comment here that we can use this critical state as a reference whether it actually exists in the flow or not.
That reminds me of what we did with sonic properties when we studied isentropic flow.
That's right, Mr. Palpatine. This is very analogous to what we did previously with converging diverging nozzles, where we used A star, T star, etc., whether they actually existed in the flow or not. So here, if we start at some state 1 and add heat, we may not necessarily get all the way to the critical value, but we'll still use this as a reference to help us solve the problem. So let's develop our equations in terms of critical or sonic properties. First, for pressure, since we already have equation 1, let's let P1 just be P, where M1 is just M for any location along the curve, and we'll let P2 equal P star, which means M2 is 1. So equation 1 becomes P star over P equal 1 plus gamma M squared over 1 plus gamma 1 squared, since M2 is 1, or taking the reciprocal, P over P star is 1 plus gamma over 1 plus gamma m squared. I'll call this equation 2. And as I said, we'll use this as a reference, even if we don't get to critical conditions in our actual problem. We'll be able to do this whether we're on the subsonic or supersonic branch. Now consider temperature. Our conservation of mass was rho 1 V1 equal rho 2 V2, but again let V equal MA equal m square root of gamma RT for an ideal gas. So rho 1 over rho 2 is V2 over V1, which we'll write as M2 square root of gamma RT2 over M1 square root of gamma RT1. The gammas and the r's cancel, leaving us with M2 over M1 square root of T2 over T1. But applying our ideal gas equation, T is P over rho R, so T2 over T1 is P2 over P1, rho 1 over rho 2. Let's use now equation 1 for this pressure ratio, and for the density ratio, we have this equation from here. So T2 over T1 is 1 plus gamma m1 squared over 1 plus gamma m2 squared from equation 1, m2 over m1 square root of T2 over T1 from this density ratio. Again, a little bit of algebra. Solving for T2 over T1 gives us T2 over T1 equal m2, 1 plus gamma m1 squared over m1, 1 plus gamma m2 squared, the whole thing squared, which I'll call equation 3. Again, we'll let 1 be any state on the curve, so we'll set T1 equal T, and we'll let 2 be the critical state, so we'll set T2 equal T star. So equation 3 becomes, where we prefer the reciprocal actually, becomes T over T star equal m times 1 plus gamma over 1 plus gamma m squared, quantity squared, where we've also set m2 equal 1 as previously for the critical or sonic state. I'll call this equation 4. We can do a similar derivation for density, and I'll leave that up to the students to show that rho star over rho is equal to v over v star equal m squared 1 plus gamma over 1 plus gamma m squared, which I'll call equation 5. Let's also look at stagnation properties. Here we'll use wise use of ratios as we've done many times before. For example, T naught over T naught star is T naught over T, T over T star over T naught star. Even though this flow is not isentropic, we're talking about state variables here. So at any state, T naught over T is still 1 plus gamma minus 1 over 2 m squared. T over T star comes from equation 4, and T star over T naught again comes from our isentropic relations, where the reciprocal is 1 plus gamma minus 1 over 2 times the Mach number, which is 1 squared, and this reduces to gamma plus 1 over 2, so the reciprocal here is 2 over gamma plus 1. A little bit of algebra, noticing that a gamma plus 1 here eliminates one of these, so we get T naught over T naught star is 2 plus gamma minus 1 m squared, gamma plus 1 m squared, over 1 plus gamma m squared, squared. This is equation 6. We do a similar analysis for the stagnation pressure ratio, which I won't show here. We get P naught over P naught star is gamma plus 1 over 1 plus gamma m squared times 2 plus gamma minus 1 m squared over gamma plus 1 quantity to the gamma over gamma minus 1 exponent, which I'll call equation 7. I typed up a final summary of all these equations for Rayleigh flow, again for an ideal gas. Our previous mass, momentum, and energy equations are shown here, along with the thermodynamics and maximum heat transfer equations we started with. The new ones here are equations 1, 2, 3, 4, 5, 6, and 7, according to our above numbering scheme. And since all these equations that involve the critical values involve equations with gamma and m only, as you can see here, these are ideal candidates for the compressible aerodynamics calculator. So I'll do an example at m equals 0.3, and for air, let's use this CAC on the website to get T naught over T naught star, P naught over P naught star, T over T star, etc. I'll compare my equations to what we get from the compressible aerodynamics calculator. Not showing my work, I get 0.34686, 1.1985, and 0.40887. On the compressible aerodynamics calculator, we scroll down until we find Rayleigh flow. Gamma is already set as a default to 1.4, and we'll set Mach number to 0.3 and hit calculate. We see the same value that I calculated for T naught over T naught star, P naught over P naught star, and T over T star. So I'll just write same here, and here, and here, making me very happy. I just want to mention that in addition to the subsonic and supersonic branches for some of these values, we also have a below Tmax and an above Tmax. And you may wonder how you can have a temperature above Tmax, so the wording is not so clear. What it really means is above Tmax means to the right of that maximum temperature point on the Rayleigh curve. In other words, in the strange zone, whereas here means to the left of the maximum temperature point, which is before we reach the strange zone. So T over T star is double valued depending on how close you are to the maximum heat case. In other words, whether you're before the strange zone or in the strange zone. If I copy this, T over T star, and select the below Tmax value and paste, I get my Mach number of 0.3. If I choose above Tmax and calculate, it jumps to the supersonic branch. If I try some value close to the critical condition for the above Tmax case, I get a Mach number of 0.967. But if I change this to the below Tmax case and calculate, I get 0.7383. This is because the Rayleigh curve is double valued up here, where for the same temperature ratio, where I put in T over T star equal 1.01, a little bit above the critical value, we had M equal 0.7382 and M equals 0.9675, a double value of M, even though both of these are subsonic. You would first get to this one, reach maximum T, enter the strange zone, and then get to this one before hitting the critical value. We also have a double value for Mach number for other temperatures like here and here, but there it's very clear since this is the subsonic branch and this is the supersonic branch. But here it can be a little tricky. Now let's do a quick example problem of choked Rayleigh flow. Air enters a 10 centimeter diameter tube at a given temperature, pressure, and Mach number. These are on the subsonic branch. And we want to estimate the maximum possible rate of heat transfer without changing Mach number M1. In other words, without changing the initial state if you try to put in too much heat as we've discussed previously. Here are our assumptions and approximations, the same ones we've been using all along for Rayleigh flow analysis. I use the ideal gas law to calculate density at 1. Then I calculate A1, which is square root of gamma RT1, from which I get 347.19 meters per second. And then I can get V1 as 173.59 meters per second. And Q dot max is when state 2 equal our star conditions or critical conditions. In other words, when the flow is choked. Thus, M2 is 1 and T02 is T0 star. So from our equations, or from the compressible aerodynamics calculator, T01 over T0 star turns out to be 0.69136, which I can quickly verify by entering a Mach number of 0.5 and hitting calculate, and there's my value of T0 over T0 star. But I used software to calculate all these values. From this, T02 is T01 over T1 times T1 over T01 divided by T0 star. And this comes from our isentropic equation for this state. T1 is given, and we just calculated this as this value. So when the flow is choked, T02 is T0 star, which becomes 455.63 K. And from here, T01 can be calculated also. It turns out to be 315 K. And then knowing both T01 and T0 star, we use our equation for Q dot max and plug in M dot as rho 1 V1 A1, and I'll write all this out with our unit conversions: rho 1, speed V1, area A1, CP for air, T02, T01, times unity conversion factors. A watt times a second is a joule, and 1 kilowatt is 1,000 watts. And our final result is thus Q dot max is 224 kilowatts. And finally, as we've discussed previously, if we try to input more than this, the whole Rayleigh curve would shift and conditions 1 would change. In the next lesson, we'll do a more general example where Q dot is not Q dot max. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.
compressible.